Welcome back to The Explainer. Today we are jumping straight into a massive, kind of philosophical gap, the space between the physical stuff we can actually touch and the abstract, digital thoughts that our computers process. We're going to do a deep dive into one single foundational question about the very nature of computing, the physical versus the abstract.
Okay, let's dive into this. The question is, can we simulate any electronic component using logic and logic gates? Now I know, on the surface, this totally reads like a standard, maybe even slightly boring computer science exam question, but really think about what it's asking us here. Can the messy, tangible, real-world reality of a physical circuit board, like the one running a vintage analog synthesizer, can that actually be perfectly mirrored by rigid mathematical code? It's like a giant puzzle.
So let's isolate the first core concept of our text, the electronic component, right? This is the physical realm. We're dealing with tangible hardware here, capacitors, resistors, actual physical currents flowing through wires. And because this world is governed by the actual laws of physics, it operates in these continuous, infinite states. It experiences stuff like parasitic capacitance, thermal noise, signal degradation. Basically, it's beautifully imperfect and just incredibly, incredibly complex.
But now, let's flip the coin over to logic and logic gates. This is the completely abstract, theoretical realm of computing, and it is based strictly on discrete mathematics. An AND gate or a NOT gate, they're purely conceptual. In this realm, a signal isn't, say, 4.9 volts with a slight hum in the background. No, it is absolutely, flawlessly a 1 or a 0. There's literally no messy reality in between. It is pure math.
And this brilliantly illustrates the fundamental clash, the tension, right at the core of our question. On one side, you have physical hardware bound by reality, and on the other, you've got abstract logic bound by flawless, rigid rules. Mapping one to the other is, well, it's insanely difficult. Just to give you an idea, to accurately simulate the physical quirks of a single 1980s microchip at the transistor level using a program like SPICE, modern computers have to run literally billions of mathematical operations every single second. And that's just to capture a tiny fraction of that messy, continuous reality.
So, the crucial point is the single word, simulate. What are we actually doing when we try to do that? Think about it. If a physical wire heats up, changes its resistance, and creates a whole electromagnetic field, but our digital logic gate only registers a pure true or false state, is that simulation actually complete? It really forces us to ask ourselves, how much of the physical world just gets totally lost in translation when we force it into this box of pure, unadulterated logic?
Which brings us right back to the ultimate boundary of abstract computing. If we ever actually reach a point where abstract logic can fully, perfectly simulate any physical electronic component without losing a single drop of that messy reality, then is there actually any fundamental difference between the simulation and the real thing? I mean, if logic can perfectly capture reality, then where does computation end and reality begin? It's a lot to think about.